Welcome back. Today we're going to look at priority queues, which is a variant of sorting that generalizes the idea to provide more flexible data structure that we can use for all sorts of applications. To get started, we'll look at the API and some elementary implementations. So a week or so ago, we looked at collections in Java and the idea of elementary data structures where we insert and delete items, and then the data structures differ on the basis of which item we choose to delete. We looked at the pushdown stack where we removed the item that was most recently added, and the queue where we removed the item that was least recently added. And then we talked about randomized queue, or a bag where we might remove a random or an arbitrary item. Today what we're going to talk about is called the priority queue. And for that, we insert items, but when it's time to remove, we consider the items to have a total order, and we want to remove the largest or the smallest item. So this little example, if we insert P, Q, and E, then when we do remove max, we want to get the Q out. If later we insert X, A, and M, then we remove max. The largest one in there is X. We insert P, L, and E, and then after a while we remove max P. So that's our basic setup. That's what a definition of what a priority queue is. So the API will look very similar to our stack or queue API, with the difference that we want to have generic items that are comparable. So the Java language for that is in the class header. We say that our generic type, key, extends comparable of key. That just means that our keys must be comparable, and we must have a compare to method that will compare it to another key. Otherwise, we have a constructor, and actually for some applications it's convenient to have a constructor that takes an array of keys as argument. Then an insert, that's put something in, like push in a stack or enqueue in a queue. Then delete the maximum. I referred to delete the minimum just to avoid confusion. We have implementation, separate implementation, usually min PQ, where we delete the minimum. Then test is empty, and we also sometimes have extra method that just gives us the value of the largest key, and also size, which is useful sometimes in collections. You might also want it to be iterable, but we'll skip that for now. There's lots and lots of applications of priority queues. Even though it emerged as a data structure relatively late in the game, now that we see that there are many algorithms that are much easier to implement when we think about the priority queue abstraction. We have data that we're processing. We can't process it all at once. We have to save it some way. And then what the priority queue tells us is let's organize it in some way so that we're always taking the best one to process next. And that turns out to be very close to a generic algorithmic design technique that we'll be looking at in many, many different applications. Today we're going to talk about event-driven simulation, which is an interesting idea that is based on priority queues, but it's also used in numerical computation, and we'll see in the algorithms for data compression and graph searching that it's useful, and in many other applications in computer science and in scientific computing. It generalizes the stack in the queue and gives us a data structure that we can use to effectively design algorithms of all sorts. So here's just a particular client that will help explain the idea. So our challenge is, let's say this is on the web. We have billions of transactions, and where they're streaming through our data warehouse or our processor in some way. And just a very, very huge number of transactions. In fact, we couldn't possibly hope to even store them all. There's trillions of them. They're coming through as fast as possible. But we're interested in the biggest ones. So maybe it's the biggest amount of dollars or the biggest cost or whatever it might happen to be. And so we can pick some number that we can store. We'd like to store the 1,000 biggest ones. So you can imagine a credit card company looking for fraud is going to care about keeping track of the largest transactions. So maybe we can store millions or thousands of them. So that's our parameter M. That's the number we can afford to store. But the total number of items, we couldn't possibly afford to store them. So, and this is just some test data where we've got all these transactions. And so we want to be able to take in data like this, and again, an unbounded stream of data. But let's say we want to keep track of the top 5 values using the third column as the value. So we're going to look at a client program called TopM that takes a command line argument, how many, in this case it's going to say 5, and then it's going to take from standard input the transactions, and it'll print out the top 5. So that's a canonical example of a priority queue client. We need to design a program that can do that. So with the priority queue abstraction, that's not too difficult to do. So we're going to use a min-oriented priority queue, so that's going to keep, it'll be one where we can delete the minimum. And it'll be generic, so we have a transaction type that holds this information, including natural ordering, where it's ordered by dollars, that last column. So we'll build a new priority queue, min priority queue, where we have the capability to delete the minimum. Then we read from standard input. We read a line, build a transaction from the information on that line, and that'll fill in the fields. And then we put that transaction on the priority queue. Now, if the priority queue has more than M items because we inserted that one, then we want to delete the smallest one there. And that way, we're keeping track of the largest M. Whenever we get a new one, then we throw away the smallest one that's there. So even with this huge stream of items coming through, we're only keeping track of the M largest item, and that's a fine canonical client for a priority queue. Now, how are we going to implement or solve this problem? Well, you can think of lots of ways to go ahead and solve this problem of finding the largest M items in a stream of N items. So, for example, you could sort them and then just look at the M at the end. But by setting up the problem, I already kind of ruled that one out because we don't have the space to sort them all, to store them all. So sort is out of the question. We'll look at a couple of elementary priority queue implementations that are straightforward. Keep the items like we would in a stack, and then when we need to find the smallest or the largest, look at them all. But that's going to be too slow. M is large and N is huge, and M times N is going to be too slow. What we'll look at is a very simple and practical implementation using a data structure called the binary heap that gets the job done in time proportional to N log M in only M space. And that's pretty close to the best that we could do in theory, and is a very important and useful practical implementation and data structure. All right, so here's just a overview of 2 elementary implementations for priority queues using the example operations that I gave before. So you can imagine keeping the items, say, in a linked list or in a doubling array, and just keeping just unordered, just as we would in a stack, just keeping them the way that they come in. We put a new item at the end of the array and remove it from the end of the array, or you could do it in a linked list. And then when it's time to remove the maximum, you have to scan through everything to find the maximum. So that's one way. You could implement this with a linked list or with a resizing array. Or you might decide, well, let's try to keep things in order, and then that might involve some work. It's like insertion sort. You have to find the place to put the new item and then put it in the right place. And again, you could do this with a linked list or with a resizing array, but then with array, you'd have to move all the larger ones over one position to fit the new item in. When we insert E, and they're supposed to keep them in order, we have to move over L, M, P, and P to get the E, N, and so forth. But the advantage of that might be that removing the maximum is easy. We just take away the one at the end. To remove the Q, we know it's at the end. To remove the max at this point, that's X, it's right at the end, and P is right at the end. So you can imagine the implementations of priority queues using these two basic strategies. Not much code involved. This is a unordered array implementation of priority queues, and it's quite straightforward. We didn't put in the, this is the cheat version where we require the client to provide a capacity, but we could easily change this to a resizing array. So insert just puts it at the end, and since it's unordered, delete maximum has to go through the entire array to try to find the maximum. When it finds it, it exchanges it with the one at the end and then removes it the same way that we would in a stack. And it'll use less in exchange just like we would in sorting methods. So that's a fine implementation if the priority queue is going to be tiny all the time. So if you, without even implementing it, you can understand this table that if we use an unordered array implementation, we can get insertion done in constant time, but we have to look at everything to delete the maximum or even find the maximum. If we keep it in order, we can find the maximum or delete it in constant time, but it takes us linear time to insert. And since, as with stacking queue operations, these insert and deletes might be intermixed in arbitrary ways, and there might be huge numbers of them, neither one of these is very attractive because they're going to take n times the number of operations. Whereas what we can hope for and what we actually will achieve is to get log n time for all operations, time proportional to log n for all operations. With a clever data structure and interesting implementation, we can actually achieve that goal. That's the basic API and some elementary implementations for priority queues.